Hey guys, welcome to Safi Max in video part 4 on the topic a particle inside an infinite potential well. In this video, I will use the mathematical results obtained in the previous videos on the same topic and will discuss the physics of the topic in detail. So I begin by analyzing the effect of quantum number n on the wave function by plotting it against position x for total width of the well equal to a is equal to 3 for different values of quantum number n. I do this plotting in Mathematica. So let's move to Mathematica. Here I have written a small program for plotting the wave function. I asked Mathematica to plot the wave function for different values of the quantum number n, and I have chosen the values n equal to 1, 2, 3, 4, 5 and 6. So I plot the wave function for 6 different values of quantum number. Mathematica gives me these plots. Notice that as the quantum number increases, the wave function becomes more oscillatory. We see that for every value of n, the wave function goes to 0 at the boundary, which agrees with the boundary condition of the problem. Additionally, for n greater than 0, the wave function also becomes 0 at certain other positions. For example, for n equals 2, the wave function is 0 at the midpoint of the box, that is at x is equal to a divided by 2. Such points are called nodes of the wave function. That is, a node refers to a point other than boundary points where the wave function goes to 0. If we carefully look at this plot, we see that the number of nodes is equal to n minus 1. Now let me put these plots at one corner of the board and let us discuss the physics behind the form of the plots. From the probabilistic concept of the wave function, we see that the probability of finding the particle at the nodal points is 0. This quantum mechanical outcome contradicts the result we obtained through classical approach in video part 1 on this topic, because there we found that all the positions are equally probable for the particle, and the probability of finding a particle at a given position equals the inverse of the width of the well. That is, we found that the probability at a position x, that is p of x, equals 1 divided by a, where a is width of the potential well. Furthermore, from these plots, we see that the probability of finding the particle is high at position where the amplitude of the wave function is large. And this is also against the classical result. So unlike the results of classical mechanics, quantum mechanics predicts that for different values of quantum number n, the probability of finding the particle at different position is different inside the well. Now there is another very important quantity related to the particle for which the classical and quantum results strongly disagree with each other. And this quantity is the total energy of the particle. According to classical result, as we found in video part 1, the energy of the particle is equal to its kinetic energy and is given by E equals half mv squared. Now for any value of the speed v, this equation says that the total energy is continuous and is 0 if the particle is not moving, that is, if the particle is at rest. On the other hand, in the quantum case, if you recall from the second video on this topic, I defined the energy through the parameter k, and we found that k is quantized, so we can write the relation between energy and k in the form k sub n equals square root 2 times mass of the particle times energy E sub n divided by h bar squared. And if I solve this equation for energy for different quantum numbers, I can write E sub n equals h bar squared times k sub n squared divided by 2 times m. And for Kn, by applying the boundary condition, we found that k sub n in fact equals n times pi divided by a. And if I substitute this value of Kn in the above equation for energy, I can write the energy into this form, that is n squared pi squared h bar squared divided by 2m times a squared. Now, if we look at equation 1 and equation 2, they are completely different, because equation 2 says that the energy of the particle is quantized due to the presence of quantum number n in this equation. And the energy is never zero because n starts from 1. For the lowest energy level, that is for n is equal to 1, this energy reduces to this form, pi squared h bar squared divided by 2m a squared. This relation means that a quantum particle can never be stationary. This lowest energy is referred to as 0 point energy and is purely quantum mechanical in nature. We see from equation 2 that there is an infinite sequence of energy levels. Furthermore, since for every value of quantum number m, there is a unique value of energy and a unique wave function. Therefore, the energy levels for a particle inside an infinite potential well are non-degenerate. This is important to note, non-degenerate energy levels for particle inside an infinite potential well. If you recall, I mentioned in the video part 1 that the quantum mechanical results for energy are in agreement with the Heisenberg uncertainty principle. So I would like to elaborate on this point here. Since by trapping the particle in a limited region, we acquire information about the position of the particle. With the information of position, according to uncertainty principle, the momentum of the particle cannot be known with complete precision. This conclusion in fact prevents any possibility for the particle to be at rest. Hence, the lowest energy of the particle cannot be zero, because for zero, the momentum must be zero, and that would violate uncertainty principle in the sense that we know the position of the particle as well as momentum of the particle, and this is obviously the violation of uncertainty principle. So, the energy of the particle must not be equal to zero for any value of n. Even for the lowest energy level, it must not be zero. This is uncertainty. This is validation of uncertainty principle. Now we can further discuss this through uncertainty principle, because the possible uncertainty and position, that is delta x, is of the order of the width of the well, that is delta x is approximately equal to a. Therefore, the minimum momentum uncertainty becomes, according to uncertainty principle, delta p is of the order of h bar divided by delta x, and substituting the value of delta x, I can write this as delta p equals h bar divided by a. This leads to the minimum kinetic energy for the particle by using the kinetic energy equation, that is k equals delta p squared divided by 2m, and substituting the value of delta p, I can write the result h bar squared divided by 2m times a squared. If we carefully look, the result of equation 6 at least qualitatively agrees with the value of E1 the energy for the ground state, which was written in equation 3.